Okay, so we saw quite a few theorems already. The last one had 10 parts, and those are actually 10 separate theorems. And still we don't know how to calculate integrals. And now comes the idea. Now we're going to start building up to the theorem that's actually going to enable us to really calculate. So here is the star of the show for today. Well, for this discussion. And the star of the show is the following. So in everything we did so far, there was a function, and it was defined and bounded on a finite interval from a to b, right? Something like this. And we asked, what is the area under the graph between a and b? That was the question. Now we're going to modify this a bit, and we're going to say, okay, what is the area not from a all the way to b, but rather from a only until some intermediate point between a and b? Let's call it, let's say, x. What's the area from a to x? Namely, what's this area here? Not all the way to b, only from a to x. So I'm going to call this area between a and x, I'm going to call it big F of x. Clearly, it depends on what x is. If you go up to here, you're going to have a smaller area. If you go all the way here, you're going to have a bigger area. It's a function of what x is. Do you agree? And what it is, well, we know what it is. It's the integral. I mean, this is like the most important integral we're going to write. I can't have it look like a sick snake. It's the integral from a, not to b, but to x. Of what? Of little f, and it's important, again, to draw your big F's and little f's differently. Big F, that's it. That's what big F is. It's the integral from little a to x of little f. Do you agree? Okay? Now, so here's our first theorem. This is not the fundamental theorem yet. Not the fundamental theorem yet, but we're building towards it. So if f is integrable on AB, then big F, which is the integral from a to x of little f, this thing, is continuous on AB. If little f is integrable, big F is continuous. Okay? The way to think of big F is as a function that kind of accumulates the area under the graph of little f. That's what big F does, right? It accumulates area under the graph of little f. Do you see that? Okay. Why is it continuous? I'm not saying that little f is continuous. I'm only claiming that little f is integrable. And by saying it's integrable, I mean I can stick it into a snake. That's the meaning of being integrable, right? Why does that imply that big F is continuous? So intuitively, the idea is that when you move little x a bit, you accumulate a bit more area. Okay? There are no jumps in the accumulation of area. The accumulation of area is continuous. Move x a little, you move f a little. When you take an x that's close to this x, how close? Delta close. The difference in the f values is going to be at most epsilon. Okay? Now that might sound reasonable if you think of a picture like this, but then you can say, wait. What if little f is, for example, not a continuous function? What if little f is the function, let's say it's 0. I'm drawing a 0 that lives up here just so you can see that it's 0. And then suddenly it becomes 1. What if this is little f? Do you agree that this is not a continuous function? Little f is not a continuous function in this drawing. This is our b, and this is our a. So little f is not a continuous function. It's still integrable. Why? Give me the shortest reason for it still being integrable. Okay, you can say it's piecewise continuous. You can say it's monotone, right? It's monotone increasing in the weak sense, right? So it is integrable. What is big F going to look like for this function? At any value x here, big F is going to be 0. Do you agree? Accumulating area under 0 is just 0, 0, 0, 0, 0. Until you get here, it's going to be 0, right? What happens when you move a bit to here? Okay, so let's say this is 1. Big F, when you move slightly beyond this point here, the point of discontinuity for little f, big F is going to accumulate a tiny little area, which is namely, I don't know if you can even see it, the area in this little region here that you obtained by moving from here to here. Do you agree? So it's still continuous. You moved a little, you gained a little area. Not 1, just this little area, and so on. Okay? So this is the intuitive kind of reasoning to try to convince you that although little f does not have to be continuous, big F is going to be continuous. Okay? Okay. So I don't want this to be in our way. This is what I want you to picture. So that's this theorem. The proof is rather straightforward from the definition of continuity. But I'm not going to write it. It's not a hard proof. And now comes the theorem I really want to emphasize. And this is called the fundamental theorem of calculus. So the questions in the audience are, I have a feeling this is going to help us calculate integrals. Well, true, but not right away. We're going to have to decipher it. Is it going to make life easier or harder? Much easier. Much easier. Guaranteed. Okay. So the fundamental theorem of calculus says the following. Suppose f from AB to R is continuous. Okay, so I'm no longer assuming it's just integrable. I'm actually assuming little f is continuous. Define, as before, big F to be the integral from a to x of little f. So little f is fixed, a is fixed. The only variable in this situation is what little x is. How far are we calculating? How far are we accumulating area? And this value, remember, for once you fix an x, you get a number. Remember? This is a number for any fixed a and fixed x. So this is a number that depends on x, a number that depends on x, a number that depends on x. That's a function of x, right? Do you agree? So that's this thing. Then, when we only assumed f to be integrable, the previous theorem only said that big F is continuous. If we raise the assumption on f and now assume that it's continuous, what we're going to get is that big F is not just continuous, it's going to be differentiable. And moreover, the derivative of big F is going to actually be precisely little f. Look what just happened here. We started off in the discussion of areas under graphs. This function is kind of accumulating the area under the graph of little f. And somehow, by some magic door, the whole topic of differentiability just came in. And moreover, it turns out that this big F, which accumulates area under the integral of little f, is just the antiderivative in disguise. That's the statement. This function, which was defined in a kind of sneaky, snakish way, is just an antiderivative. Its derivative is little f. Do you see that? So that's why this theorem gets the honor of being called the fundamental theorem of calculus. It ties between two subjects that at first can even be considered two different subjects. Differential calculus, derivatives and all that's related, and integral calculus, and suddenly we see that they're two sides of the same coin. Okay? So what I want to do is first intuitively convince you why this is true. Then I want to prove it. And then I want to show you a corollary of this, which is called the Newton-Leibniz formula, which finally tells us how to calculate integrals. And I have a wild guess that you've met it before. You just didn't know how exciting it is. Okay, so first of all, the intuition for this thing. So let's go back to the drawing we had here. Okay? So remember, f of x is the area from a to x. It's this thing. Let's look here, not at x. I want to make this even bigger. Or with this, okay, I can do with this. Let's look here. This is x. Let's look at x plus h. I moved just a bit from x. This thing is just a bit. I'm making it big so you can see it from back there, but I just moved a bit. Okay? So, what is the area all the way up to here? Well, before you say it explicitly, what's the area from a all the way to x plus h? It's capital F of x plus h. Do you agree? So, capital F of x plus h, which is all the area from a all the way here, minus capital F of just x, which is the area from a only up to here. So this difference is this area. Does everybody agree to that? Everybody? Good? Okay. But at the same time, this equals, well, not exactly equals. This can be approximated by, this thing is kind of rectangular-ish. Do you see that? What is an approximation for this thing? Well, a reasonable approximation would be the value of the function. I need to choose a point. Let's take the point x. Okay, the value of the function at x. Oops, orange. The value of the function at x, so this is the rectangle, times the width of this subinterval, which is what? H. So this almost equals, it's an approximation for little f of x times h. Do you agree? Let's divide both sides by h. What do I get? I get f of x plus h minus f of x, capital F, divided by h equals, well, squiggly equals just little f of x. Do you agree? But what is this thing? As we take h's smaller and smaller, in order to make this statement precisier and precisier, there's no such word, right? This is, again, squiggly equal to f prime. Do you agree? So that's the intuition. This is not a formal proof. These squigglies make it not formal. Okay? But this is the intuition of how suddenly f is related to the derivative of this function that accumulates area. Good?
Can you please do that last graph again?
From here to here?
Yeah.
From here to here, I just divided both sides.
The first one.
How I got this? I calculated the area of this rectangle in two different ways. One by saying it's the area under the graph all the way up to here, minus the area only up to here. That's this side. Do you believe that?
Yeah.
On the other hand, I said, think back to Riemann sums and the way we approximated areas. We took the width. The width is x plus h minus x. It's just h. Times the height. The height is f at the point x. That's this. Good?
Yeah.
So this is the intuition for the fundamental theorem of calculus. Now, let's go back here. This is the fundamental theorem of calculus. Now let's prove it. Let's prove it formally. Okay? So, proof. What do we want to prove? We want to prove that big F prime equals little f. So what is big F prime at the point x? Okay. So I want to prove that it equals little f at the point x. Okay, so need to show. What is big F prime? I'm going to go to the definition of the derivative and apply it on big F. Okay? So what's the definition of the derivative? It's the limit as, so I want to show that this holds for any x. That's the statement. So I want to show that this is true for any x, so I'm going to fix an x0. And I want to show this for any x0 in AB. Right? This is what I want to show. Do you agree? So what is the definition of capital F prime at x0? It's the limit x goes to x0, capital F of x minus capital F of x0 divided by x minus x0. This is this. Do you agree? If I calculate it and show that it exists, in particular, it would say that f is differentiable, and I want at the end to get this as the answer. Right? So it turns out that in order to calculate this, I have to calculate the two one-sided limits separately. So I'm going to first do this limit, and then the other one I'm going to tell you just do it on your own. It's very similar. So what is this limit? This is the limit as x goes to x0 plus of what? What is capital F of x minus capital F of x0? It's the integral all the way up to x minus the integral only up to x0. Do you agree? So it's the integral from a to x of little f minus the integral from a to x0 of little f, all of this divided by x minus x0. I just plugged in what capital F is. That's how we defined it. Right? What's the difference of these two integrals? As we said before in the intuitive picture, so it's the limit x goes to x0 plus. What's the difference between going all the way to x to going only up to x0? It's the integral from x0 to x of f divided by x minus x0. Good? Everybody good? Okay. And now I'm going to use what we previously called Theorem 9 in the list of theorems that we had in the previous hour. Namely, it was the theorem, the intermediate value theorem for integrals. And by sheer coincidence, it's still on the board. There it is. So somehow it's the only one that survived over the break. So this is a reminder of what it is. If you have a continuous function on a closed interval, then the integral of that function equals the value at some intermediate point times the length of the interval. Okay? So I'm going to use this at this step. Okay? Look at it. Now look back here. So instead of writing the so limit x goes to x0 plus, down here there's still x minus x0, but now up here, instead of writing the integral from x0 to x of little f, and remember, f is continuous, therefore it satisfies the condition of that theorem, which required a continuous function, I'm going to write f at some intermediate point c times x minus x0. Do you agree that this is precisely using that theorem, which we actually proved based on its previous theorem, which we proved based on the previous theorem of that, which eventually we didn't prove because we didn't want to go down to the actual definitions? Do you agree? Does everybody see how we use that theorem? Now, but there's a little delicate point here. C, you get a different C for different x's. C is between x and x0, between a and b in the original theorem, right? So C is between x and x0. x0 is fixed. But x approaches x0. For different x's, you get different c's. Do you agree? So I'm going to call this C sub x. Okay? C sub x, in order to emphasize that it's not a fixed C, it's a C that depends on x. Okay? This equals, these two cancel, so we just get the limit of f at cx as x approaches x0 plus. Right? Because these cancel. But what is cx? Cx is some point between x and x0. As x approaches x0, here's x. Here's x. Here's x0. Cx is somewhere in between. That's not going to work either. I actually need, this is what we're going to do. Here's x0. Here's x. Cx is some intermediate point. Do you agree? As x approaches x0, what is Cx forced to do? To approach x0 as well. Do you see that? So the limit of f of Cx as x approaches x0, Cx approaches x0, and since f is continuous, when Cx approaches x0, f of Cx approaches f of x0. So what we showed is that the limit defining the derivative at x0, well, the right-sided limit is this. You can do the same thing for the x approaches x0 minus and get the same value and conclude this fact. So I know this proof may be a bit challenging. That's okay. It was important for me to include it because this is, after all, the fundamental theorem, and I want to show you that nothing is magic here. Okay? If you need to go over it again and think about it some more or ask, that's fine. That's good. And you can ask now if there are questions. But it's important to actually see that this is... And once again, you can see the difference between a formal proof, and an intuitive argument with the squiggly equal signs, which may be very, convincing, but it's not formal. Okay? And doing non-formal math can lead to loss of points, for example. That's one thing. No, but it can also lead to, well, in some cases, missing the general facts, in other cases, even mistakes. Okay? So math is formal. And behind everything we do, even when we just argue it informally, there's always the formal layer, which we sometimes don't do in detail. Yes?
Why does when f of cx, when x approaches x0 plus, equals x?
Do you agree that when x approaches x0 plus, c of x approaches x0 plus? Do you agree to that? That was what I tried to draw with, what I tried to exhibit with the markers.
I didn't understand that.
C of x, this c of x, back to this board. This c of x is between x and x0. Do you agree? So when x approaches x0, c of x is forced to approach x0 as well. It's trapped between the two ends. Do you agree? Look here a second, please. This board. Yair, thank you. When c is between a and b, in our case, c of x is between x and x0. Do you agree? When x approaches x0, c of x, living in between, has no choice. It approaches x0 as well. Do you agree to that? Good. Now, back here, if c of x approaches x0 and f is continuous, and it's essential in this theorem that f is continuous, then f of c of x approaches f of x0 by definition of continuity.
You're missing a sandwich.
It's not a sandwich. It's the definition of continuity. C of x approaches x0, f of c of x approaches f of x0. That's the definition of continuity. No sandwiches.
What he said was like sandwich by saying that cx is on the right side by x0 and on the left side by x.
Okay, that's not really a sandwich. That's... Okay, if that's what you... it's not exactly the sandwich theorem. The sandwich theorem relates to functions. Okay, we're not... That's... Okay, I understand what you mean. Good? Question, yes.
Shouldn't it be then as c of x approaches x0, not
As x approaches x0, c of x also approaches x0. That's the statement. Therefore, f of c of x approaches f of x0. Yes?
Why is it necessary to do it also from the plus and also from the minus? Why can't we just do it?
Well, if you do it from the minus, then x is smaller than x0. So here it's not going to be an integral from x0 to x. It's going to be an integral from x to x0, because x is on the left. And it's going to boil down to a very, very similar argument, except you're going to have to pull out a minus sign and cancel it at one point. It's going to turn out the same thing. Okay, you can't write it at once, because it won't be correct. Maybe you can with some absolute values, but I don't know. Okay? Okay. So, now that we know the fundamental theorem of calculus, and we proved it, let's go back here and see the statement. Questions, ask me. I know she explains much better than I do, but please not now, okay? Question?
No, it's just
Okay, ask her later. Okay, fundamental theorem of calculus. Corollaries. Things we can deduce from this theorem. Corollary number 1. Corollary number 1. Forget all the intermediate stuff here. You took a continuous function, you concluded that it has an antiderivative. Do you see that? Every continuous function has an antiderivative, is the derivative of something. This is not a trivial statement in its own. Clear? You took a continuous function, did some magic via snakes, and you found an antiderivative, a function whose derivative is the function. Good? So that's a corollary. Now we know that you draw a continuous function, even if it looks strange, it has an antiderivative. Not always do we know how to find the antiderivative explicitly. We mentioned that when we talked about antiderivatives. We know how to do integration by parts, and we know how to integrate rational functions, and we know how to do substitutions, and we know all kinds of magic tricks. But there are some functions which have antiderivatives, and we don't know how to find them. Okay? So let me remark that. Remark. Every continuous function has an antiderivative, remark, although the antiderivative is not always nice. For example, it's not always an elementary function. It doesn't always have a nice formula. Okay? So for example, where is that thing? Here it is. So for example, there are some classic examples. Maybe I even mentioned some of them. So for example, sine x over x is continuous on, let's say, the open interval 0, 1, or on 1, 2, doesn't matter, it's continuous, right? You can make it continuous on R if you define it to be 1 at 0, right? Therefore, it has an antiderivative. But there's no nice formula for the antiderivative. We just know it exists. You can write it as the integral from a to x of this thing. That's the antiderivative. Okay? Hmm? Taylor would only give you an approximation. You'd still get an approximation. There'd still be a remainder. Okay? It doesn't have a nice closed formula. Doesn't have one. It's not that we don't know how to find it. One can actually prove that it doesn't have one. Okay? And some more of these, oh, I hope I remember them correctly. I think that sine of x squared, they look innocent, right? They don't look dirichleish, right? They look innocent. And yet they don't have elementary antiderivatives. They have antiderivatives, but we don't know formulas for them, and they don't have nice formulas for them. Okay? I think this one is of that form as well, and there are more. Okay? So they're continuous, therefore they have antiderivatives by the fundamental theorem, no formula. Okay? So if somebody comes up to you when you're studying for the final and says, hey, can you help me solve this integral? First ask, dude, where did you find the integral? Before somebody just gives you an integral to calculate. Because it might be that it's an integral that just is not that easy to solve, exactly. Okay, so that was corollary number 1. Corollary number 2 deserves a board of its own. So corollary number 2 is called the Newton-Leibniz formula named after these two great mathematicians and scientists. And I'm going to phrase it the following way. Let f from AB to R be continuous. You can relax these conditions a bit. And let big F be an antiderivative of little f. Then, and here's the million-dollar statement, finally, the integral from a to b of f of x dx equals, and now no existing c's or whatever, take the antiderivative f, evaluated at one endpoint, b, and subtract the antiderivative evaluated at the other endpoint. Do you agree that this is beautiful? Beautiful. Okay? That's it. Now we know how to calculate integrals. Give me a function. Give me any function you want. Well, not any, because we know that some of them are tricky. But give me nice, friendly functions that are really nice and friendly. I will secretly go to the side, calculate the indefinite integral, find an antiderivative, come back and say, ooh, plug it here, subtract, you're done. Okay? So this is denoted, notation for this thing. This is just notation. Notation. F straight line A, B. That's how I'm going to denote it. There are other notations. Okay? This is the way I'm going to denote just the difference. F at B minus F at A. That's the notation I'm going to use. Okay, are you familiar with this? Mm-hmm. Good. Okay, so I still need to prove this. This is going to follow in 2 lines from the fundamental theorem. Okay, so let's prove this. So maybe before we prove it, let's do an example. Before we actually prove it. So example, suppose I want to calculate the integral from 0 to pi over 2 of 2 plus cosine of x minus x squared dx. Diving into the deep water. Remember, all we knew how to do so far was what? A constant function in x. How's that for a next step? Well, not too hard. This equals, I need to find the antiderivative. In this case, the antiderivative is what we called an immediate antiderivative. What's the antiderivative of 2? 2x plus sine x minus x cubed over 3. That's the antiderivative, right? So in this case, it was an immediate step. In other cases, you may need to do some calculations here. I'm not saying it's always for free. This example is for free. And then evaluated between 0 and pi over 2. That's it. The snake is gone. Do you see that? Okay, so here I used Newton Leibniz.
I think you forgot the plus c.
No, I did not forget the plus c. The statement is,
Since you just wrote down the antiderivative.
an antiderivative. An antiderivative. When you say plus c, you say there's a family of functions. All of them qualify as antiderivatives. That's true. Take any one of them. An antiderivative. Use that. If you want to take this thing and add a 5, that's fine. It's going to cancel out. And you're going to, but why take it? Take the one without the constant. Okay, now what do I get here? Okay, so from here, it's just plugging in values. That's the easy part, right? So the deepest theorem is somehow hiding in this step, which I'm sure many of you have done many, many times already. Right? It was just given to you as some formula, magic formula. Now you know, well, we still didn't prove how it stems from the fundamental theorem. We do that in a second. So what do we get here? We get 2 times pi over 2. I'm going to do this annoyingly with all the details, just for this example, so everybody follows, plus sine of pi over 2 minus pi over 2 cubed over 3. That's the antiderivative evaluated at b, minus 2 times 0 plus sine of 0 minus 0 cubed over 3. That's the antiderivative evaluated at the lower bound here. Good? So what do we get? Here we get pi plus sine of pi over 2 is 1 minus pi cubed divided by 8 times 3 by 24. And all of these are just 0. So that's the answer. That's it. Now I need a volunteer. Jeff. You do this now using Riemann sums. Start. Go. Hmm? Come on. Do it. We're waiting. 7 years later. Are you done? We're all still waiting.
5 plus 1 minus 5 cube power 25.
He got it. Good. You got this? Good. Great. I'm amazed. Very good. Good job. Okay. You do not want to calculate integrals using Riemann sums. Only if you have them on homeworks and you have to. Okay. This is much more user-friendly. Do you agree? Everybody? Okay. Let's prove how the Newton-Leibniz formula, how we get the Newton-Leibniz formula from the fundamental theorem. Let's prove that. Short, very short. So, proof. Proof of the Newton-Leibniz formula. I think these are the letters for Holland, for the Netherlands, right? Oh well. For us, it's Newton-Leibniz. Okay. So define. Remember what we have. We have a function, a continuous function. We chose any antiderivative we wanted to, called it capital F, right? That was the theorem, the corollary. We chose n antiderivative, capital F, which secretly we found by solving the indefinite integral, and plugged it in. That's the formula. So now I'm saying define g of x to be what we previously called f of x, because f is now taken. So g of x is going to be the integral from a to x, not of little f. Okay? This is what we previously called big F, but big F was now taken. So call this g of x. By the fundamental theorem of calculus, g prime equals little f. Do you agree? That's the fundamental theorem. It's still on the board there. Good? Everybody? Okay. Hence, there exists C, a constant, such that such that F equals G plus C. Because F is an antiderivative, G is an antiderivative, therefore they differ by a constant. Do you agree? Everybody? Say yes. Okay, questions? Yes?
What's F in our...
F is the F from the theorem, an antiderivative that you somehow magically came up with. for example, by calculating the antiderivative in all the methods we had before we had that little case of amnesia temporarily. Okay? So this is satisfied. Therefore, f of b minus f of a. What is f of b? F of b is g of b plus c. G of b plus c minus g of a plus c. Do you agree? F equals this, f at b is this, f at a is that. Right? C's cancel, so we get g of b minus g of a. G is this thing. So it's the integral from a. What is g of b? G of b is the integral from a to b of little f. Do you agree? Minus the integral from a to a of little f. True? This is 0, so we just get this, and we're done. The integral from a to b of f is f of b minus f of a.
Where do you get the a to a?
This thing?
Yes.
It's just g of a. What is g of a? G of a is putting a here. So it's the integral from a to a, and that's 0. That's how we defined it. Good? Okay.
Why do we need all the middle stuff?
What do you mean all the middle stuff?
Like, why do we need G?
Well, we wanted to prove that. Okay, are you suggesting an alternative proof?
Maybe.
Oh, go for it.
Why can't we just say f of b minus f of a is equal to the integral from a to b of f?
How do you know that? F is not this. No, 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 no. F in this, okay, I maybe confused you. In this corollary, F is not what F was in the fundamental theorem. F was an antiderivative of little f. Okay? That's why I use G here for what F was in the theorem. Okay? F is no longer this thing. F in the corollary is just an antiderivative. G is this one. And I have to go via this one. Okay? If that confused you, I apologize. That maybe was not a good choice of letters. I should have maybe called that one G, but it's so standard to write it with F that I couldn't. That would be really... Okay. Okay. So what I want to do next time is do many applications of integration. Okay. So first of all, we're going to see some more methods of solving integrals. They're all going to boil down eventually to using this Newton-Leibniz formula. But we're going to see how we do integration by parts, indefinite integrals, and how we do integration by substitution in the definite integral context. And then I want to show you more applications of integrals that may seem completely unfamiliar to you. So not necessarily areas under graphs anymore. From physics, from other areas in mathematics like calculating lengths of curves and things like that. We'll do that next time.